All right, so welcome back to our course in cyber physical systems. Today we're going to start covering chapter 4 on an introduction to the Internet of Things. And in this chapter, we're going to focus on 3 topics. First, we're going to give you an introduction of what exactly is the Internet of Things. What do we mean from a technology perspective? And then we're going to discuss 2 technologies that are thought to be very important to the coming about of the Internet of Things paradigm. One is radio frequency identification, so RFID, and the other one is wireless sensor networks. If we go back to the last chapter, where we covered extensively the definition of cyber physical systems and a lot of ideas on applications and how these systems can play a role in our lives, at this point we can categorically define a cyber physical system as a system that has collaborating computational elements coupled or controlling physical entities, including people. So we saw in the last chapter that these systems are or can be everywhere. They can be everywhere. And we talked about some of these domains, but we can find these complex systems in aerospace, automotive, chemical processes, civil infrastructure. We talked a lot about transportation. We talked about energy and healthcare and manufacturing. Again, transportation, entertainment, and of course, consumer appliances, so gadgets. And the systems link computational and physical elements, and they're also linked to each other. They are networked. And if we have enough of these systems networked together, then we have what we call an Internet of Things paradigm. In that sense, and in that context, the definition of Internet of Things is a network of physical objects or things that can communicate with each other to exchange data with other devices that are equally connected. Now, a couple of things that are key is that each thing in this network can be uniquely identified. And we're going to see that because RFID, that you don't need to be connected to the network to be identifiable, and somehow if that's the extent of the role that this thing plays in the network, then that's enough, and the object or the thing doesn't need to be actually a communicating entity other than being able to provide its ID. So that's what we're looking at, these 2 technologies, RFID and wireless sensor networks, which could be equally wired sensor networks. But since we have wireless technology available, widely available, and wireless is more convenient and make things more accessible from an implementation perspective, we're going with wireless sensor networks. That's what makes sense. So we'll be able to identify each unique object on the network, even if it's not a communicating entity. If you are a communicating entity, clearly you can be identified because you are on the network. But then you can be a front for other objects or things that only communicate from an RFID perspective, and they still can be identified, although they are not active communicating agents on the network. All that can be, that information can traverse the internet, which is available, and it can interoperate within that infrastructure. So that's what the Internet of Things is. Some historical background: the internet dates back to around 1970 from a project originated by DARPA. We discussed DARPA a couple of chapters ago on how they fund important technological advances, mainly with military applications, but it was developed mainly by universities, funded by DARPA because of its applicability to the military domain, but it was developed by universities, so it actually stayed an open network. And during its development, since its origination around the 1970s, became available around 1980, and around 1990 really took off, exploded, and here we are, right? So this global network of interconnected computers use what is called the Internet Protocol Suite Stack, TCP/IP, which stands for Transmission Control Protocol / Internet Protocol. So that's what TCP/IP means. And right now, it is estimated that more things already are connected to the internet than people. There are people in the planet, with a large percentage of people in the planet being able to connect to the internet, if they are not necessarily continuously connected, like in the more developed economies. So this vast internet network is consists of millions of private, public, academic, businesses, and government networks that are globally deployed. So they connect via different appliances, like gateways, for example. So from a hardware perspective, some of the hardware that is employed in configuring and deploying the network are routers and gateways. Those are two different types of networking appliance. Routers, their main mission is to route traffic, and a gateway serves as a hub of a subnet to the wider network. So a gateway is a router, but not the reverse. A router is not a gateway. From a software perspective, we have the TCP/IP stack, which until somewhat recently, just a few years, it was on its version 4, IPv4, and now we are really going through the transition to IPv6. And that takes years. There is a lot of legacy equipment and software that doesn't support IPv6. A lot of network appliances, computers, and software installations, now they support both. Okay? So that's just, as we have discussed, that's just good systems engineering to be able to support widely entrenched legacy technologies. There are many benefits and new features in IPv6, but one of the most salient ones is the number of bits in the IP address. So the the IP address of IPv4 is 32 bits, which is about 4 billion. You can have 4 billion addresses, unique addresses. But that's not going to be, there are more than 6 billion people in the planet, and if each person eventually, the majority is connected to the internet and they have several things, you can see how you run out of addresses. So one of the reasons, one of the drivers for IPv6 is the greater availability of unique addresses, because IPv6 employs 128 bits of for the IP address. So that's about 3 times 10 to the 38, whatever that is. It's a big number. If I type this, I can see that, for example, my computer supports both IPv6 and IPv4, and you can see the address for IPv4. It's altogether 32 bits in the 128 bits IPv6. So right now my computer can connect with both, whatever is supported. So another aspect, of course, of the internet is the symbolic names, DNS, the domain name system for symbolic names, which are linked to an IP address by gateways and routers. So with that idea of sort of what the internet is, now let's talk about the other side. Let's talk about the thing. Very formally, actually, from a strict language definition. So the thing is an object. It can also be an idea. So a thing doesn't have to be physical, but it's something that exists. Okay? Now, an object is something physical. Something physical. So that has, we may refer to it as the Internet of Objects, but an interesting idea is, if we're calling it the Internet of Things and some things are not physical, how would that really plug into that paradigm, into that network? So an object is a thing, but a thing may not be an object. Something physical. People are physical things, they're objects. And specifically, when the Internet of Things idea was conceived, what the conceivers of that idea were thinking was things as an objects, as everyday things. Things that we take for granted, they are available. So if we add the ability to connect, to communicate, we can come up with a lot of new ideas and products based on the connectivity and the data availability, our ability to harvest data from these things that are now connected to this network. And then, once they are on the network, these things can communicate with each other. They can interact with human in the loop interaction and react and control and make life easier. So again, from a historical perspective, the Internet of Things was coined as part of the Auto ID Center, founded in 1999 and based at MIT. A big part of the work of that center, of that lab, was RFID technology. The work on RFID technology, which still is one of the most underutilized technologies, but is very well utilized on a lot of things, such as asset tracking and the pervasive toll booth tax, right? So that's where it comes from, and it has stock and is growing. So if we have this global infrastructure and we assume that eventually we can tag all these objects, things as simple as razor blades, car tires, and we can collect data. We can collect data without necessarily knowing what we're going to do without it, but the data is there. It's up to us to come up with services, applications, and products that can utilize that data for the betterment of society. If we have that, because we can put this very inexpensive, very tiny chip. So we're going to see about RFID in the second part of this chapter, and we're going to see that we have really a transponder, a chip that is actually an RF transmitter and receiver, about, I would say, 9 millimeters square, so that's about 3 millimeters on the side. And the biggest part of it is really the antenna, because we have to radiate, and that controls how much distance we can cover to be identified and respond to the query. But if we can put, because these things are so inexpensive, if we can put it anywhere, on soda cans, different parts of cars, so we can get an instantaneous account on when each part was put into the car, if there were repairs, or if all the original parts are in a car, and track different types of objects and equipment and assets. It's really up to our imagination to come up with, for an application for the technology. So here we're just talking about the technology. We talked about some applications in the last chapter, applications of cyber physical systems, but the field, in my mind, is wide open. It's up to us to seize that capability of the technology and come up with great applications and products. I'll give you a tangible example later on. So, as I mentioned, some of these objects will have their own IP address. So if they are connected to the network, they will have their own IP address. And they can be identified by that IP address. So that's one part. And that network can be a subnetwork with a gateway from a wireless subnetwork. When we talk about wireless sensor networks, that's what we would be talking about, a subnetwork that is wireless. But eventually, if you want to transcend great distance, we're talking about a global network. Of course, at some point you have to tap into the non-wireless part of the network, whether it is actual copper lines or fiber or some other means of transcending vast distances, which could be wireless also if we're talking about satellite-based communications. So the objects and things that are connected to the network in that fashion will have their own IP address and can be identified. But then each of those could be a front for any number of other objects that communicate through this using it as a mini gateway, and the access of these objects are through RFID technology. And all they can do is identify themselves and more. When we see about RFID technology, there is an important feature of RFID that is not only the identity of the object, but also you can store data. So each RFID tag actually is a memory. How much memory and things like that depends, and of course factors into the cost. There are some that have very little memory and it's mainly an ID, but some of them have quite a bit of memory. So like the RFID chips that are used in Europe for passports, they have a lot of information in those tags. So, but we'll come back to that. So the idea is that you can have your own IP address or not, but you will be able to identify yourself through that address or through some RFID tag information. So, as any new and great technology, as I mentioned, it really is up to our imagination, and anything that can revolutionize the world can be used for not necessarily for good, right? So we need to be responsible, and hopefully we won't be touching too much on the ethical and societal issues, because this is an engineering course. But it's worth mentioning that there is always, with any great technology comes great responsibility, and we have to be mindful of that. Privacy issues, for example. We see a lot of that in the news with some other technologies. But we have to be mindful of that. And that can only happen through judicious regulation. So important that the people in charge of the regulation, they are aware or are more technology savvy than classically they have been. So I'm going to stop here, and I'm going to play this YouTube video that is pretty cool. And let's see if the audio comes through. I'm not sure.
The origins of the internet date back to the 60s with the initial experiments about computer communication systems. From the very beginning, it was conceived as a global network to exchange information and digital content without restrictions of time or distance. Over the last years, internet has evolved at an exceptional speed. Currently, there are about 2 billion people connected to the network. With the advent and proliferation of mobile devices, the way how we access the internet has also changed. The number of electronic devices that can be connected to network services has increased dramatically. But internet connectivity is also possible beyond these devices. Every object around us may be connected, collecting, processing and sharing information. The Internet of Things opens up a new world of infinite possibilities. Can you imagine using running shoes that are able to upload to a website the time, distance, speed and calories burned during the activity? And what about this information being stored on the internet to track your progress over time? Can you imagine wearing a t-shirt connected to the internet, mirroring changes in your social network or displaying alerts about your favorite topics? Can you imagine your son interacting remotely with children from other countries or cultures through an internet-connected toy? Day after day, there are more objects and devices that use the internet, which contributes to the creation of a smarter planet. It is estimated by year 2020, there will be more than 50 billion objects connected to the internet, an average of 6 devices per human on Earth. Smart apparel, social networks, health, furniture, sensors, smart cities, buildings, toys, quality of life, people.
So, a bit dated, but still, I think it's relevant. So, and it's short enough that, you know, why not show it? So we'll stop here and we'll pick this up tomorrow. Okay? So thank you so much.